Dear students, welcome to the basic genetics class, and this is a continuation of our unit 1 week 1 where we are discussing elements of heredity and variation. So in today's lecture, which is the lecture 3, we are going to understand the Mendel's data. So we already discussed how Mendel was able to look at the P data, and he postulated his 4 different postulates, and out of them we made, later on scientists made 2 different rules. So in today's class we are going to understand what were the statistical method of understanding this data. So in this today's class we are going to discuss probability, product rule, sum rule, binomial expansion and factorial. So let's talk what is the importance of probability, why we are talking about probability when we are talking about understanding the data in genetics. So remember that genetic inheritance follow chance-based event, right? So I will reiterate it multiple times in this lecture that when we have a tall or a dwarf plant, we do see capital T or small t as factors or allele, and there are equal chances of getting either capital T or small t. So that is what we have discussed in previous classes, but today we are going to talk about the more statistical basis of that. So let's take the example of a coin toss where there is a head and a tail, and if you toss a coin one time, then there are equal chances of getting either head or a tail. So we can say that 50% chances of getting head or 50% chances of getting tail, or they have 0.5 frequency each. Similarly, as I just said, in case of gamete formation means when an individual parent is having 2 alleles for one character or one gene, capital T, small t, which denote their height, you can see they can make 2 gamete, capital T and small t, right? So individual gamete can have either capital T or small t, and then having capital T or small t, we are having a chance of 50-50. So now come to the rule, the first rule that I am going to discuss, which is the product rule. Remember that this product rule is also known as AND rule, right? So what is AND rule or product rule? The probability of 2 independent events happening together is the product of individual frequencies, right? So what we are seeing here, in the same coin tossing example I discussed before, that probability of getting head in one coin toss is 1/2, right? So if you toss a coin one time, either you get head or you get tail. And if I ask you to do the toss once again, then again you have a chance of either getting head or getting a tail, right? So then the possibility of getting 2 heads is 1/2 multiplied by 1/2. So remember that, right? So 2 independent events happening, and in these 2 independent events, what we see is that we are multiplying the probability. Similarly, with the example, because we have to understand it for genetics, we can see the same thing happening when we are talking about the gamete formation, right? The male can give capital T, small t. A female can also give capital T, small t. And if somebody asks you what is the probability of having 2 T's, capital T's or 2 small t's together, what is it? So it is a multiplication of each probability. 1/2, 1/2, 1/2 for capital T, 1/2 for another capital T coming from mother, and then the multiplication gives you 1/4. Now come to the other rule, which is addition rule. Remember, this rule is called as either or, because sometimes eventually you may get little confused when to apply addition rule or when to apply product rule. I'll give you some clarity during my talk, but at least remember that multiplication rule is an AND rule and addition rule is an either or rule. So the probability of either of the 2 mutually exclusive events happening is the sum of their individual probability. So how we will understand this example? You see, again, I will take the conventional example we were discussing the earlier, coin tossing. So earlier I said toss a coin once, toss a coin another time. What now I am asking you? Probability of either getting head or a tail. What is it? So, either you can get head is 1 by 2, or you can also get tail. If you are just tossing a coin once, 50% chances are there that you get head and 50% chances are there that you get tail. So, if you sum these probabilities, then you will get 1, right? So, these are the only two possibilities that you can get, head or tail. Those are the two options that you have, and either or you have both the options. Either you get head or you get tail, and that is why we are doing sum. Remember, in case of frequency, we are saying 0.5 plus 0.5, right? So, if we take another example and make the example a little more complicated and say that let's toss 2 coins simultaneously. So, now you're not having 1 coin, you are having 2 coins, and we ask you the question, what is the probability of getting 2 heads or head tail, tail head, or 2 tails in these 2 coins? So, to understand this example, what you will see is that if this is the coin which has one side head, another tail, same way the other, you toss it, you have 50% chances of getting head and tail in both the coins. And getting head, remember, we are applying, what we are going to apply here is the product rule, because you are going to have head and head multiplying the possibility 1 by 4. Same way, getting 2 tails together is 1 by 4. Pay little more attention to this head and tail example. So, you can get head and tail, head from one coin and tail from another coin, right? And the possibility is 1 by 2. You can also get the same thing, tail or head. Now, tail from the first coin and head from the other coin. And so, ideally it's head or tail or head, they are same thing, but you have another 1 by 4 possibility of getting this combination, and that is why we are applying sum rule. So, you have 2 possibilities but mutually exclusive to get head or tail, and that is why we are doing sum, and finally we are getting the probability of 1 by 4, 1 by 2, 1 by 4, which is 1 is to 2 is to 1. So, you can see this is matching with Mendelian genotypic data. So, now let's take this example with the gamete formation exactly the same way. We have a heterozygous male parent, a heterozygous female parent, and getting capital T and a small t from male, 50-50, same way for female parent, and then same way getting tall means capital T together is 1 by 4, means multiplication of half and half, same way for small t, and now for so this should not be head and tail, it should be T or T or T or T, right? So then you get these 2 alternatives 1 by 4, 1 by 4, and finally it is 1 by 2. Same way, exactly the same way as we discussed the coin toss example, and final ratios are 1 is to 2 is to 1. So now let's discuss some real problems where we are going to apply multiplication rule and addition rule together, and I hope that you will remember that product rule or the multiplication rule is an AND rule and addition rule is the mutually exclusivity. So take now the example of a real-time example where we are talking about a disease or a character where we are talking about albinism, and so we have parents which are heterozygous for albinism. So albinism is caused because of a recessive allele. So when the 2 recessive alleles come together, then only you see the phenotype. So what we are asking in this question is that parents are heterozygous for albinism, as you can see here, and they have 3 children, right? So what they want you to address is, what is the probability that these parents have all the 3 children with albinism? So remember, whenever you solve these kind of problem, you need to know what are the all possible outcome from across. So from a heterozygous cross, we already know that we are going to get 3:1 phenotypic ratio we are talking about. Then we are going to get 3:1 phenotypic ratio where we have 3 normal children and 1 child with albinism, right? Because capital A will be normal and these will be carriers, but mostly they are normal, right? Phenotypically they are normal. We'll consider them normal. So now what we are seeing? We are seeing that we have out of 4 possibilities, there are 3 children that have chances to be normal and 1 is going to be albinism. So do remember that when we talk about the probability of normal, it is 3/4, and when we are talking about the probability of albinism, it is 1/4. So having all the 3 children with albinism, what it will be? The multiplication of the probability of how many times we are going to get albinism, which means 1/4, 1/4, 1/4. Means every child can have a probability of being normal or albinic. Being normal, it has a probability 3/4, and having albinism, it has a probability 1/4. So we are multiplying because they are asking us to tell what is the probability of getting albinism. We are going to multiply the albinism related probability, and the final answer is 1/64. Now add one more question to the same existing question where the parents have 3 children. Now what we want to ask is, what is the probability that 1 child has albinism? Remember, this is now getting little complicated. 1 child has albinism and 2 children are normal. So, a parent could have 1 child at a time, right? So the first one can have albinism and rest 3 could be normal. So what you would do, let's see this, look at the first possibility. First child is having albinism. What is the possibility of getting albinism? 1/4. And being normal for rest of the 2 child, 3/4, 3/4. Same way, it is possible that first 2 children are normal. So 3/4 into 3/4, and the third child is having albinism. So 9/64. And there's another possibility that the first child is normal, the second one is having albinism, and the third child is again normal. So you have this possibility of having 1 child normal and 2 abnormal. There are 3 different ways to get it, mutually exclusive. So what we would do is we will sum all these 3 possibilities, and then the final answer will be 27/64. So you can see in a real-time example how we can combine the product rule and addition rule to solve these kind of questions. There's another way. See, if somebody is asking you for 2 children or 3 children, it is easy to address by that because you know how many combinations you can get. But if there are more children, then by making these kind of different combinations, you may end up missing something. So there are 2 additional ways that you can solve the problem. So one way is the use of binomial expansion. So what is binomial expansion? We learn it in our 10th grade, that a plus b, the whole square of a plus b is a square, 2ab and b square. It's exactly the way we are going to expand our binomial for a power of 5, like 5 children or 6 children or whatever number, right? So let's take this example. So I'm just keep it simple. I'm just keeping the example same. What I'm doing is I'm increasing the number of children, right? So again, there are parents that are heterozygous for albinism and they have 5. Remember, in the previous example we have 3, but now they have 5 children. And what the question is asking you to solve is, what is the probability that 2 children have albinism and 3 are normal? So out of 5, 2 should have albinism and 3 should be normal, right? So binomial is a mathematical tool that is often used in genetics to predict the probability of different genetic outcome, and usually we apply for those traits that are inherited in a Mendelian way. So it is it may take another 3 or 4 minutes for you to understand how we are going to expand this binomial. But remember, so here we were, what we are doing is we are replacing P plus Q. We are replacing A plus B with P and Q. And so what is P? P is the probability of one event, right? And Q is the probability of alternating event. So what is one event, what is alternating event? Your choice. You can take P as a probability of being normal and Q as a probability of being a child with albinism. And what is N? N is the number of times this event occur. Like 5 children, we will put it 5. So I'll take it, step by step. We'll talk about the easier example first, and then we'll make it for our example that I have written in my slide. So if we want to expand this binomial, how many terms? What are the terms? Is a square plus 2ab plus b square. So there are 3 terms. So you can see that is how we are expanding. So how many terms are going to be there? How do we know that? So what we do? So to expand the binomial, we make a plus. N plus 1 is the number of terms that we are going to get. So for example, if there are 2 children, n is equal to 2a plus b whole square. How many terms we are going to get? 2 plus 1 is equal to 3, mean a square 2ab b square, or p square 2pq q square. So do remember one thing, that these individual terms have a position. We'll talk about it. So now let's take the example that we have, that the parents have 5 children. So how we are going to expand? How many terms we are expecting? 6. And how we are going to expand these terms? See, when we have these 5 plus 1, 6, we have 1, 2, 3, 4, 5, 6, 6 terms written here. And as I said, each term, we are naming it as term, has a position number. Now the question is, how you will know what will be the exponent? So what is the exponent? Exponent is this, right? And what will be the coefficient? What is coefficient? Coefficient is this. How we are going to determine this? So let's learn one thing at a time. We'll talk about how we are going to determine exponent. So to determine our exponent, remember that the exponent of P, we will take P first and then we will talk about Q. So to have the exponent of P, the first term is always the power to which the binomial is raised. So there are 5 children. So the first power should be P5. Right? And the second, we continuously decrease the power of P. You see P5, right? P4, P3, P2 and P1. So P1 is P and then P0. Okay? And what we will do for Q? So if we want to go for Q, what we will do? The first power for Q is 0. Right? So P5, Q0 is P5. And then Q1, Q2, Q3, Q4 and Q5. So P is decreasing and Q is increasing like as a power. And how we are going to determine the coefficient? When we are determining the coefficient, what we do? Remember, the coefficient of first term is always 1. That is why it is 1P5, which is P5. The coefficient of second term is always the same as the power to which the binomial is raised. So, the coefficient of second term, see here, we are talking about this coefficient, from where this 5 is coming. So, this 5 is coming because the binomial is raised to 5. So, 5 is we are putting here. So, that is simple. First coefficient was always 1, second coefficient is always the power to which the binomial is being raised. Now, come to the little complicated part. How come we are getting this number 10? So what we are doing here, we are multiplying. To get the coefficient for term 3, what we are doing is, we are looking at term 2. So when we are looking at term 2, what we are doing is, we are multiplying 5 with 4. We are multiplying the coefficient with the power. So we get 5 into 4 and then we divide it with the term number, which is 2, and that is how we are getting 10. And same you will do for subsequent terms. You get the third details for third term. So what you would do to get the fourth? 10 into 3, 30 divided by 3, 10. So that is how we continue going, and then that is how we are going to calculate the coefficient. So now again, because we have learned how to solve the binomial, let's talk about problem again, that the parents have 5 children and we want to know what is the probability of having 2 albinism and 3 normal children. And we already discussed that there are 3 by 4 chances to be normal and 1 by 4 chances to be albinic. And if I consider it as a 3 by 4 as P and 1 by 4 as Q, up to you, you can switch, it doesn't matter, and apply the binomial here, then you can see where are those things where P, power of P should be 3 and power of Q should be 2, because we said we want the 2 albinism, which is Q, and 3 normal, which is P. So we need to just solve this term 10P3Q2, and when we solve this we will get the answer. So it's as simple as that. And I'm just covering a last quick point that sometimes things get even more complicated and even binomial expansions getting difficult, and in that case you can use factorial. Now it is also simple. So how we solve factorial? This is the formula for factorial, where P is the overall probability of an event, right? And N, you already know that probability of one event, right? Like 5 children, so N should be 5. And Q and, well, let's solve it here. S is what? S is the P event occurring how many times? So normal child, how many times? Albinic child, how many times? So S is that, and T is the same thing for the other event. And P to the power S is the frequency of P to the power time it is going to occur, and probability of Q and the time it is going to occur. And the same way, just the same example that I had before, we can solve like what is the probability of having the same thing, the 3 normal and 2 albinic child. So total factorial of 5 divided by 3 factorial and 2 factorial, and then 3 by 4 to the power 3 and 1 by 4 to the power 2. So how we solve factorial, that is the one last thing that I need to tell you, is factorial. Solving the factorial is simple. You just keep on reducing the number to 1. So 5 into 4 into 3 into 2 into 1 is a factorial of 5, and factorial of 3 is 3 into 2 into 1, and factorial of 2 is 2 into 1. And then if you solve it, you will get the same answer of P.26. So this is exactly the same example that I have shown you here, and you get the same answer here. You can solve it this way, or you can solve it with factorial. So with that, I'm going to sum up, and towards the end, I want to give you some activity and discussion questions so that you can solve, and if you have any difficulty, you can definitely write in the chat box or directly to me. So what is the question for you today? If parents heterozygous for albinism have 6 children, I just raised the difficulty level a little, then you need to answer what is the probability of these parents having 2 children with albinism and 4 normal. And the second question is, what is the probability that second child has albinism and rest are normal? So I hope you learned some new aspects of stats to understand genetics. And if you have any questions, feel free to write me. I will be happy to help you. And with that, I thank you all for your attention.